There we go. We're live on YouTube now. So, as I said, today we are going to be doing a bunch of sorts, and that's pretty much going to be the entire day. There will be practically no coding today, probably, since much of these sorts I'm just going to show you how they're done visually. We're going to go from, like, I wouldn't say easy to hardest, although it would look a little bit like that, but more of like from the slowest to fastest algorithms. And by fastest, I'm talking about sorting time, not growth rate in terms of slowness, right? And so what I'm going to do for each one is I'm just going to give you an example of how it works so you all kind of get it. And then I'll talk about the asymptotic complexities, which I showed last time, that bigocheatsheet.com to go there, so you can look at them, but I'll also write them down, and I have them here. And yeah, I have a bunch of examples. So yeah, let's just kind of go with that. And let's us begin with the one that we all hopefully already know, which is bubble sort, right? So let's go bubble sort. So even though you know bubble sort, there is one very important thing that I would like to mention about bubble sort, which you may or may not be aware of, depending on, I guess, if it was just ever brought up. So bubble sort is a slow algorithm. It turns out that the big O is n squared, the theta is n squared, and interestingly enough, the omega is n. Now, that's interesting because you might be like, ooh, that's really fast, linear time. Yeah, but the omega of bubble sort is when you already feed it a sorted list or an almost sorted list, or like, well, the best scenario is you feed it a sorted list. But bubble sort will finish faster if the list is almost sorted. Like you have 1 or 2 digits that are unsorted. So yeah, but most of the time, as you can see by the theta, bubble sort is going to be an n squared. And of course, that's the slow algorithm for sorting, because last time we were talking about the lower bound of comparison-based sorting, which is going to be n log n, right? And so, you know, that is going to be your best case scenario for the big O. So n log n is better than n squared. So we know that this is not that good. But it's easy to code, right? How do you code this? Well, you just do 2 for loops that iterate from the beginning to the end of a list. So you do like for I is equal to 0, I is less than n, I plus plus, and then you do another loop instead of that says like for j is equal to 0, j is less than n, j plus plus, and then, well, technically, you don't, the second one, you don't do j equals to 0 for the initializer, you do j is equal to 1. And then for the last digit, you make sure that you do, for the outer loop, that you also don't do the last digit. So you might do, you know, I is less than n minus 1, just so you don't go out of bounds. And as obvious as that seems, I actually screwed that up in the first assignment of the 202 section this semester. And there were, you know, if you go look at the 202 Discord, there were some weird discussions there about like a random number appearing in my sorted thing. And it turned out because it was going out of bounds and just picking up some weird random thing from outside of memory, which was actually a 0 in my case, because I guess memory was being nice. So yeah, something trivial might be something easy to forget. But anyways, the idea visually how bubble sort works is that if you have a bunch of numbers, so for example, you know, you can go to Geeks for Geeks, by the way. I'll leave the description below the link for YouTube, and for you guys, let me post it on Twitch right now. So Geeks for Geeks has really, really good sorting pages, like descriptions of each of the sorting algorithms I'm going to talk about today. So I encourage you to go check them out. They also have animations to look at the sorting sometimes if you watch the videos at the bottom, which are pretty cool. And finally, Wikipedia actually is pretty good too with the sorts, because they have this little GIF in some of the sorts. Not really, I guess, bubble sort, I think. Or do they have it? No, they do have one, yeah. So if you go to Wikipedia and you scroll down to the, here, let me screen share actually. So if you go here, and this is just a Wikipedia for bubble sort, as you can see up there, bubble sort. And what you do is you just look here. This thing is actually showing you how the sorting works. So I'm not going to go over this example because you can see it's a different one. but I'll go ahead and do another one. Yes, embrace the sorting feed. There's tons and tons of videos of people on YouTube. In fact, when we get to quicksort, I'm going to show you one method of quicksort, and then I'm going to send you a link to watch a video to learn a different method. You only need to know one for the test, so you can do the one that I show you, but the second method is cool, and some people like it better. So, I'll send you a link to that as well. It's already on Canvas, by the way, if you want to go ahead. But yeah, Wikipedia is actually good for the sort because it has those animations. And then this is Geeks for Geeks, just so you can see what it looks like. So yeah, I could do the same exact example, but you get nothing out of that. So I'd rather just pick random numbers and do that instead. But yeah, so just very quickly, so you visually see how bubble sort works, to make sure that you all remember that. Let's just put some random numbers in here. A few numbers. Be very spooky if I ended up with the same numbers that I had somewhere in like old examples, but I'll try not to. So, okay, that'd be weird. Let's see. We almost had the same digits, so there's a 5, 1, 4, 2, 8 in that one. We have a 5, 1, 4. Oh my God, yeah, we do have the same digits. It's just in different order. That's weird. Okay, I don't like that. That's weird. Maybe subconsciously, I just know that. I am not kidding either. If you go Geeks for Geeks, they have 5, 1, 4, 2, 8. Oh, yeah. Okay, let's just make different numbers. We can do duplicate actually. Yeah, duplicate is nice to see what happens. Okay, good enough. So let us go ahead and sort this using bubble sort. So as I said, there's two for loops. So usually what you do is you have your for loop. I'm not going to write the entire, like I said, I don't really want to write code today, but your I is going to go to n minus 1, and the other for loop is your j is going to go to n, and then your I is less than n. Your initializer, sorry, for this one is I is equal to 0 and j is equal to 1. Just so you don't start both pointing to the same spot, and then they both do the I and j plus plus, okay? So something like that. And then there's the reason why I want to show you this piece is because like all you have to do here is do a swap between the I and the j component. So if you have this in an array, you would pass a function where you basically are passing a I and a j by reference so that this thing can swap them and whatnot. But another thing that you can do here to optimize quicksort to actually achieve the omega scenario is you put an if statement outside of this loop that says like if no swap, or you can say if not swapped, then just break out. And what this is going to do is you want this swap function to, I don't know. I mean, there's a lot of ways you can do this, but I guess if you want to keep this as really short as possible, you can make that swap function return 1 whenever it gets called, and then just set that to some boolean called swapped that gets true. So really all I want to do is set swap to true. So that what I'm trying to do here is, and of course you got to put an if statement here, don't forget. Say like if a sub j is less than a sub I, that's an I, not a j, the second one, then call a swap, okay? So what I'm doing is I'm saying if the number after the one I'm looking at, so if I'm looking at two numbers and I want to see which one's greater than the other one, if the one after it is smaller than the one before it, then you got to swap them, right? And so the idea is you do these swaps to fix it. And I'll show you really fast an example in a minute. But the idea is that if you go through an entire pass and you do no swapping, that must mean the list is sorted already. So rather than keep going the two for loops all the way to n each, which would be n squared, by the way, why is it n squared? Remember, nested loops, right? That's that analysis that I showed you like week 2. That's how you get that n squared from this, and that's how you get this numbers. But yeah, so essentially if you break out of the loop the first pass you run, which is just checking it n time, 1n, then that is a way to check if the list is sorted. So basically, if you ever do a swap as you iterate through a pass, that means that something changed, which means that you're not possibly done. Whereas if you do an entire check and nothing changes, then that definitely means you're done. So that's what this little Boolean flag is doing to break out. So that's just an efficiency thing for quicksort. If you don't do that little Boolean check, then this would be omega of n squared as well. So that's one of the things you can do to optimize it. The other thing you can do is you don't have to start every time from 0 for the loops, like when you're bubbling up. You can actually start, like as you sort it, you know that like the ending of the list is already going to be sorted. Every time you do one iteration of bubble sort, one number gets sorted. And so if you are on the 5th iteration, the last 5 digits are sorted. So you don't need to look at those anymore. You can just stop at like the 6th one to the end. That's another optimization thing. That one is just making it a little bit faster, but it doesn't change the asymptotic complexity. If you want to see examples of code for that Geeks for Geeks I think has an example. So you can check it out. So on the line swap equals swap I, that is essentially true if it runs that function. Yeah. So I'm just saying that my swap function will return true whenever a swap happens, which of course is when I call the function. So yeah, I'm just basically setting it to true. And make sure that you set it to false at the beginning of the for loop up here. So you set swap, so you initialize swap to false here. That way, it's like, okay, I'm going to do a new pass. Let's see if something gets swapped. Okay? Yeah, so just return a Boolean or something. So, all right. But yeah, let's look at that with actual numbers just to make sure that you all remember this. So you start out with your I and j. So your I and j are looking at these 2 digits. And you're going to compare both of these and see which of them is greater than the other one. So, you say if what j is looking at, so I and j, so what j is looking at, if that is greater than the I value, if it's less than the I value, swap it. If it's equal, you don't need to swap because they're both the same. But if it's less than, then they're out of order, right? That's one way you're looking at it. Another way you can look at it and say, if I is greater than j, then swap it. Okay? Or that's one way, or you can say if j is less than I, right? It's the same thing. It's just basically the 2 checks could be either saying, and by I I'm saying the contents of that. So if a sub I is greater than a sub j, that's when you call your swap function, right? But you can also rewrite this like literally just flip it around and say if a sub j is less than a sub I, then swap it as well. So either of these are the same thing. I'm literally just flipping the whole thing. You can see that, right? Like, that's the same thing as that. So yeah, either of these will work. And so in this case, that's the case, that we actually need to call swap. So then this is going to get swapped with this. By the way, you all remember how to do a swap, right? You have a temporary variable, you copy one to the temp, then you assign one to the second one that you copy to the temp, and then you copy the temp back to the variable, right? So 3 lines of code for swapping, unless you're doing some really fancy stuff, which you can do. But at the end of the day, you're still somewhere in memory using a temp. So anyways, when you do that, what you do is you shift this ahead, right? So you start shifting it like that. And so ultimately now you're going to look at these 2 and compare them and see, okay, do I need to basically bubble this again? And so you compare and see, okay, well, what about 9 and 5? Well, 9 is greater than 5, so you need to go ahead and move this around like that, right? And then you basically keep going and going and going and so on until you get to the end. So in this case, this gets bubbled up. And then again, this moves here, and then this gets bubbled up. And that's that's when you finish like an internal loop, basically, of this, okay? And so at that point, because you did at least one swap, it means you're not done. So then you go back to the beginning. So now you're going the second time around in the loops here. And so you start looking at the comparison between them. So 1 and 5 are correct, so you don't need to swap. This is good. So here's, okay, this is interesting. So here they're equal. So when they're equal, you don't want to swap. If you do swap, your sorting algorithm is going to still work, but you're going to lose a special feature of bubble sort called stable sorting, which I will talk about when I finish this example of bubble sort. Okay? But if you swap these 2 values that are equal, you will lose the stable sort of feature of bubble sort. So you don't want to do that, okay? Make sure you don't do that. Oh, and by the way, technically speaking, I did screw this up. This should not be an I. This should be a J, and this should be a J plus 1. I'm just thinking that as I'm doing that. I said an I there. So really, you know, consider this your j and j plus 1. Because otherwise, you're doing like some weird form of like another sorting algorithm, actually. So I don't know if anybody noticed that. Nobody said anything. It's kind of sad. You all should know bubble sort. But yeah, that's the comparison you want to make. Because as you see, the two numbers, if it was I and J, then like you would always be looking at this in comparison to other things. So that actually would be more like an insertion sort, basically, or actually no, like a selection sort, which you'll see. It's like in like 20 minutes. But yeah. So yeah. But anyways, okay. Hopefully you'll have used bubble sort. But anyways, the point is that when you're looking at these two, so j and j plus 1, then you don't want to swap them because you violate the stable sort thing. Okay, I'll explain what that means in a minute, but let's just keep going for now. So here you do want to swap because you have your j being less than j plus 1 essentially. So you know, you swap these two like that. Yep, okay. And then after that, you move on. So here's the catch. If you do the simple version of bubble sort, you would still do this check between the 5 and the 9. If you do that extra thing I'm talking about, where you keep decreasing the end value that the loop can run into every time you run it, then you would actually not do the check here. You would not do this check. You would know to stop now because it's the second pass that we're running. So, yeah, it's a good thing to do that for efficiency purposes. It's going to be a small efficiency gain because it's not going to change the asymptotic complexity. You're only going to be doing like, it's still going to be n squared, but like it could be n squared divided by 3 or something. Okay? So, but anyways, you finish this pass, but because you did swaps, you're not done. So you go back to the beginning. You check these. These are good. These are not good. So these are going to get swapped. And then you keep going. You check. Technically, at this point, you don't need to check these and these because, again, this is the second pass. So if you did that efficiency thing, this would stop. But let's say we don't. So we check this and be done. You still did a swap technically. Now I know the list is sorted, but the algorithm doesn't know that. It's because you did a swap, there's a chance that it's not sorted yet. Like, when would it be an example that it's not sorted? An example if would be like this was 15259. Let's say that we change this 2 to a 0. Okay? In that case, in this pass, we would have swapped the 5 to the 0. And as you see, that's not sorted, right? So the algorithm doesn't know whether or not this thing is in the right spot. It just knows that it should go before this one, but it doesn't know if it's in the right spot. So that's just a quick example as to the why we need to do one more pass. Now, it just happens to be that right now it's sorted, but that may not always be the case, as you see with the top example, okay? So, yeah, you know. So we do that extra pass, but now this time, we look at this, it's sorted, this is sorted, but technically, at this point, this is the third pass, so we would not need to go. But again, if we do the simple version, we check all of these. See that everything is sorted in the sense that there's no swap required. So now our Boolean flag never returned to true, or it never came true that we swapped something. So then we can call the break statement and get out. Otherwise, this would have run one more time, and then it would have done nothing, and then it would be none. Okay? So yeah, that's bubble sort. Hopefully that is all review. But let's talk about the stable sort, which is the reason why I actually bring up bubble sort. Because bubble sort, while it's not that fast of an algorithm, is a stable sorting algorithm. And so stable sorting is a very interesting feature that you want an algorithm to have. I think that the Geeks for Geeks might have a stable sort page. Stability and sorting, yeah. So definitely want to check that out. But it kind of explains a little bit about it. It has a formal definition that they list there. Let me actually write that down here. It says a sorting algorithm is stable if I is less than j and a sub I, it has equalities there, equivalence, a sub j implies is less than pi j. However, This is not very clean as to what it means. They explain down there, they say like that this is a sorting permutation. Sorting moves AI to IJ, and oh God, what is the symbol? It's so tiny. Oh, I can't even see it. But let me kind of explain to you what it really means. Will I post the link in the Discord server? So these links I'm posting right now in the chat. But if you're watching on YouTube, they'll be on the description of the YouTube video. But yeah, so let me explain in layman terms what this means. So when you're sorting a list, like the one we did before, so like I don't know what it was, but there was 2 5s, that's what I remember. So let us say that this sort that we're doing is not just any numbers, okay? Let us say that these numbers are actually student ID numbers, like NC ID numbers or something, okay? So for example, student 1's name is Steven. Student name 2 is Jorge. Student name 3 is Tony. Student 4 is, I guess, Voden, 64. And then student 5 is, okay, I wrote one too many O's, but that's okay. And then we have, I should have picked like your guys' names that are short, but it's okay. All right, so we got these students that we're sorting through, okay? And so, let's say that we're trying to sort these values, and they're not, right now they're sorted, but like, let's just mix them up a little bit. Let's just say that we do something like that. And that's good enough, actually. Okay, so there's the list, all right? So as we sort this, suppose that we first want to sort alphabetically, okay? So if we sort alphabetically, we're not sorting the number, we're sorting the letters. In that case, whatever algorithm we do, we are going to end up with the following list. So see, C goes first, and then probably the J. And then from there, we got the P, the S, and let's make this a little smaller so that we can fit them all. And then the T and the V. Okay? So now that it's sorted alphabetically, let's sort numerically. Okay? So here's the interesting thing about this. When we sort numerically, notice something about the 5s. If I move it like this together without changing the order the 5s were in, this will be sorted numerically. However, when you have duplicate values, so duplicate keys like these 5s, the way that these are going to be sorted is going to be alphabetically. So when it comes to duplicate keys, we don't lose the internal sorting that this was done ahead of time. Okay? So that can be very, very useful when you're trying to sort by multiple values. So for example, you might want to sort things by NCID, but technically NCIDs you won't have duplicates, right? But suppose you're trying to sort people by age, and these are people's ages, they're all really young. Then you might have people that have the same age. So then you have to decide in what order do I want to sort those. So you might want to be like, well, they're already sorted by age, so I sort by name. So when you sort them by age, keep the same ordering of that. Or you might actually just want to keep the ordering for other reasons, like if the order of numbers are just all over the place, and it's random, but you still want to keep the same order of the duplicates, even though they're random, then the stable sorting will do this. So the stable sorting will guarantee us that the 5 and the 5 don't get changed. Whereas in the other scenario, if you're doing a sorting algorithm and it doesn't care, it might actually put these in this order, because technically speaking, this is also the sorted list when you're just thinking about the number, right? And so in this case, the V and the T got messed up. So that's what in layman terms like sorting means. It's essentially stable sorting. It's essentially sorting a list without changing the position of the duplicate keys when you're sorting that. Okay? And it's not going to be relevant at all when all you're sorting is a single value. So if you're sorting a bunch of numbers, that's it. If you're sorting a bunch of letters, that's it. But when you're sorting an object, think 202 days, when you're sorting an object based on a specific field of that object, such as a name, an ID, an age, whatever it is you're using as your key to sort, you may care about not changing the order of the duplicates. Okay? Now, suppose that you are trying to sort something that is made up of first and last names. Okay? So let's say that here we have the following. So we're actually sorting a person called Steven, Jorge R, A, I don't know, Tony DE, Voden, I guess 64 is their last name, and then you had a number next to your thing, didn't you? Okay, it's out of the screen now, so we'll just do TO or something, and then yeah, we have actually we'll to prove this point I'm going to need somebody else in here. So okay, so then actually we kind of need to give you a last name, so we're just gonna call it TI, like the TI-85 calculators or something. Okay, but let's throw in another name. Let's say that you have a twin, and for some reason they named it the same as you, but that twin's last name is different, TO. Okay, or maybe these are middle names. I don't know. Here's the thing. Suppose that I tell you, I would like you to sort these names alphabetically by first name, but then if you have duplicates, I want you to sort those duplicates by last name, okay? One way to sort this and avoid all these issues is to compare the entire name string, like first and last name, and then that would actually work. But suppose that you could only look at the first or the last name. You can't look at both at the same time. Stable sorting will fix this for you. So what you want to do to figure this out is you want to sort by one of the names first. So let's say you sort by the first name. Actually, no, let's sort by the last name first. So in that case, let's say we have DE. Well, the 64 technically is going to go first, right? Well, it depends on what you think about numbers, but I'm just saying numbers go before letters. And then we have a lot of T's in here, actually. So RA, and then T. Oh, there, sorry. I was trying to remember the alphabet. Okay. So now that it's sorted by last name, let me actually copy this because I want to leave that this time. Oh, that's cool. Can I do that? Yeah, okay. That's no, it doesn't do it quite as cool as I thought it would. Vader 64? What? That's not. Okay, yeah, that messes up the names. All right. So Vader 64 sounds like a cool Nintendo 64 game. Oh no, I think we crashed something. Oh, there we go, it's back. I thought it crashed. Okay, so let's go ahead and sort by first name now. So as we sort by first name, in this case we have this going first, and then from there we have these two, right? So in a stable sorting algorithm, these two are going to be kept in that same order and be moved here. Okay, and then we do the rest, which will be that, and that, right? And so if you look at this compared to the original list, well, not the original, but the first path that we did on the last names, you can see that we have the names correctly sorted by first and last name. Okay? Oh, yeah, good point. Sorry. Like I said, I don't remember the alphabet right now. So yeah, you can see that the first and last name is going to be okay if it's stable sort, because all we're looking at in the second pass is the first names. So if it's not stable sort, then some algorithms do not guarantee that these two duplicates are going to be kept in the same place. So you may end up with a situation where you have something like this. And if that's not what you want, then that's going to screw it up, right? So stable sorting can come in useful when you actually care about keeping things in the same order when there's a duplicate. So it's only going to matter whether an algorithm is stable or not when it comes to duplicates, okay? Again, even if you have a sorting algorithm that's not stable, you can somewhat make it stable by just checking every single field that you care about keeping stability on, which in this case would be like, okay, don't just sort by one field, sort by both fields, okay? So yes, stable sort is nice because you do avoid the redundant swaps. However, you know, like the time complexity matters the most, right? So if I tell you, okay, I have an algorithm like quicksort, which is not stable, by the way, and it's n log n time for most of the sorting situations, and then you have bubble sort that's stable, then, you know, I'd rather like handle the extra compares afterwards than like go with bubble sort, right? So stable sort is like a nice feature to have, but it's not particularly going to dominate compared to the time complexity. But yeah, with all things given the same, you do want to get stable sort. Also, like you said, when it comes to space, you know, less swaps can be nice too. Yeah. It's not going to affect whether your computer crashes or not. If your algorithm is bad, it will not. It will die. It will kill the computer anyways. But yeah. Okay. So that's stability for sorting, and as you know, as I go over each of the algorithms, I'll tell you whether it's stable or not, because you know it's good to know. And just as a spoiler alert, when it comes to merge sort and quick sort, they both n log n, but merge sort has stability, so that gives it a bit of an edge. Although quick sort is technically a little bit faster. So yeah, pros and cons. There's no one good answer for these kind of things. Okay, let me see if there's nothing else that I want to mention on quick sort. And by the way, you can see all in Geeks for Geeks, there's implementations of bubble sort if you don't remember it, in like 50 different languages. So you can look at that and like have fun. Optimized implementation. Yep, we talked about the optimized implementation. Geez, they do have a lot. Whoa, why is the C# optimized so long though? Jeez, that's scared. It looks longer than like merge sort. Ooh, PHP, nasty. Oh, okay. This might be interesting to look at. So, what is the worst case scenario? Yeah, worst case scenario, bubble sort. Yeah, Microsoft. This is interesting with bubble sort. It turns out that a lot of the algorithms, the worst case scenario is the sorted list, but reversed. So like, if you're trying to sort 3, 2, 1, that's the worst case scenario for n equals to 3 of bubble sort, because you have to do a lot of bubbling. Every time you bubble, you get one thing in order. So like, if you have it in reverse, that means that the biggest number here has to go all the way to the end, right? I think it'll make more sense if I add more numbers in here. So like if you have this, you can see how this has to literally swap like all the way here. And then this has to swap all the way there. And then this has to swap all the way there. So you're basically guaranteeing that every single comparison you do is going to require a swap, and that you're not going to be able to cut corners, because it's going to take n iterations to do each item in the right spot. And so, well, n minus 1, because at the end you don't need to move the last item. Everything else will be ordered right. That's something interesting to think about. With bubble sort, the last pass, everything should be okay, because at that point there's only one number left and they should be in the right spot because everything else is in the right spot. So by deduction, if you have 10 items and 9 of them are in the right spot, then the 10th one has to be in the right spot. Otherwise, something else wouldn't be on the right spot, right? So that's optimization as well. Which, yeah, but yeah. So the worst case scenario, reverse. It's bad for bubble sort. So yeah, I mean, that's just a thing to know. When you talk about space, like I said, we don't really talk much about space, but technically, all you need for bubble sort is, you'll see it as either O of 1 or O of n for auxiliary space kind of thing. This is just talking about how much space you need for a temporary variable for the swap function. You technically only need one spot, and it's a constant. It doesn't matter regardless of the size of the list, because you just need one temp anyways. Sometimes you'll see it as O of n because they're saying, well, you need the space for the list, but not really anything else. So both of these kind of signify the same thing. Another term that you will hear when you're looking at algorithms is whether the sorting is in place or not. What that means is that, for example, with bubble sort, if you have your list in an array, so like this is your list you're sorting, you can just swap things around within the same array. Yes, you need that one extra temp variable to work with, and of course you need your I and your j's and all the other for loop variables, etc. But what I'm saying is those are all fixed in size. You only need one extra spot to be able to work with this. The data itself is always going to remain in the same array. Whereas like some algorithms require you to make a brand new array and then to insert things as you go. So like, okay, I'm gonna insert one thing, I'm gonna insert the other one, and so on. So when you do require extra space and you can't just like mix things in the same spot. So what I'm saying is like, imagine you got a deck of cards and you got a table and you say, okay, you have this table, you can't use more space in the table because the table is your sort of your initial space. If you can sort things in there, around, then you're good to go. That's sort of in place. But if you need to make a brand new table to start copying things over there, that's not an in place sort algorithm. And that's relevant when it comes to space complexity, because in place means that you don't need extra space, which for a massive list might be a benefit. It's still n times, but 2n versus n with space might be like 2 terabytes instead of 1, which can be considerable. So yeah, I mean, it's still n at the end of the day, which is why, again, we don't care too much about space. But there might be some algorithms like logo sort, I guess, that might require more space if you're actually just keeping a new instance every time you make a randomization of it. So yeah, that's pretty much it. Okay, moving on. The next one we are going to do, and I always get these two mixed up, insertion and selection sort, is going to be insertion sort. Okay? Oh, wait, let me move this beneath all this stuff. There we go. So first of all, let me just link you to the Geeks for that. If you're curious, you can check that out. Insertion sort. And again, the Wikipedia one probably has a little GIF animation of it. And what to say about insertion sort? You can look at the code from insertion sort, but I guess let us start by sort of telling you how it works. Like the best example that people think about with insertion sort, and I think Geeks for Geeks even says this, is the deck of cards when you're playing like a card game. So when you're playing a card game, and I should have brought some cards or something for a sorting class, but I don't really play cards, so I don't really have cards anywhere. But yeah, so when you have a deck of cards in your hands, if you've ever played cards, I like somebody gives you like a 5-card hand, and so you're sorting your cards, and you take a card and you insert it in the right spot that it would belong, and then you keep doing that for all the cards until they're in the right spot. That, as the name implies, is insertion sort. So let me just show you an example. Let's do letters. That way we guarantee we're not doing the same example as other times. So X, J. Oh, you know what? Here, I know how we can randomize this. Let's just pick a name from you guys and sort that. So let's do the fox. We're just going to assume that's an O. And just because I would assume the 3 goes before the numbers, but let's just do an E for that. Okay? So we're doing this. This came from chat. So we're going to sort your name by ascending order. Okay? The way you do it with bubble sort, with insertion sort, is you're going to keep track of an index. Okay? And that index, you can call it I or J or whatever. And you're going to also keep track, actually, yeah, just one index is fine. And so what you're going to do is you're sort of going to, you're going to iterate through the list. So you're going to work your way to the end. And as you do that, when you see a letter, you're going to look to your left. So kind of what you've already sorted, and insert it where it belongs. Okay? So you can think about this as a second part of your list over here, this magical second part of the list, okay? And that's going to grow as you look at numbers. So you look at the T and you have nothing. So at this point, you just assume that T is part of your magically sorted list. Okay? After that, you look at the H. Your job now is to take this H and put it in the spot that it belongs within your magical list. In this case, there is only one letter, so this could either go before it or after it. In this case, it goes before it, so it's just going to go there. Okay? All right. Next, we are going to look at the E. So we look at the E, we grab the E, and we insert it wherever it belongs. So it could go here, it could go between these, or it could go after. In this case, it's going to go in the beginning of it, and again, our sorted list grows. Now, this might seem like, wow, this is so efficient. We just have to pass, we're going to just do one pass, and by the time we get to the end, we're done. This is really fast algorithm. I'm going to start doing this forever now. It's a little bit misleading part. Look carefully. Yes, this is going one at a time, but when I grab this and I tell you, well, you got to put it in the right spot, you're like, oh yeah, well, it's going to go there. You can see that very easily, but the computer can't see that very easily. What the computer needs to do, I'm going to show you with this next one. When it looks at the O, what it really does is it goes to the beginning of the list and it starts comparing it. It says, is O greater than, less than, or equal to E? Well, in this case, you need to check if O is greater than E. If O is greater than E, then keep going. All right. If O is greater than F, keep going. Okay. If O is greater than H, keep going. Okay. If G is greater than H, keep going. Well, now O is not greater than H. Okay. If it's not greater than H, than T, then it must go before it. So then it's going to essentially throw it in there and then keep going. So every letter, as it looks for where it's supposed to go, that is going to potentially take n time. And I'm going to, the name is perfect, man. It was destiny. Because now you're going to see that happen with this X. You have to check, is X greater than E? Yes. Is X greater than F? Yes. Is H greater than X? Yes. If O is greater than X? Yes. Sorry, well, I said it wrong. If X is greater than O? Yes. If X is greater than O? Yes. We're done with nothing else, so it means it must go after. So we had to check every single number of our sorted list before we found that it was good to go. That's n, technically. Well, it's n of the sorted side, which is going to increase every pass by 1, right? So this becomes kind of like an n times n plus 1 sort of scenario, I think. I have that somewhere here. Or n times n minus 1. One of the two. But ultimately, if you do the math, that's just going to be also n squared, okay? So it turns out that the insertion sort is indeed going to also be n squared, like that. And technically speaking, it's going to be n squared in all cases. I don't think there's an omega of n for this one. Let me triple check that on my list, but I think it not, because it would still, like, even if you feed it a sorted list, when it grabs this number and it starts looking, it has to look through all those things. So I think actually the worst case scenario is ironically giving it a sorted list already that's complete. So I don't think there's a scenario that you can achieve with the n for this one. Yeah, insertion sort n squared all around. So all three of these are going to be n squared. So it's worse than bubble sort, technically speaking. But ironically enough, it's popular as a quick algorithm to just kind of take care of things. Like just throw things in and we're good to go. Call it a day. It's also very easy to code. Let's just finish the example now. So we got LOL left. So the LOL is going to go here. So technically we look at the L, we compare with the E, with the F, with the H, and then with the O. And then we're like, okay, O is greater than L, so it must go before it. And then let's talk about stability. Stability is the other thing. Is this going to be a stable algorithm or not? Well, let's see what happens when it looks at a duplicate. Again, I'm glad this name had a duplicate in it. So when it comes to the duplicates, this right here was before this O, right? Because it's already been in the sorted section. So when we start from the beginning here, we go one at a time, and then we hit duplicate. So we have to be a bit careful here. If we put it before, we have broken the stability, right? Because they're out of place. However, there's a very easy fix for that. Just put it at the end of all of the existing duplicates. So in this case, this is a duplicate, and this is not. So then you put it there, okay? So as long as you're a bit careful about duplicates like that, you can make this a stable sorting algorithm, okay? You just have to have that little extra code, basically. Yeah, okay? Yeah, greater than or equal to. Yep. So yeah, I'm pretty sure that will take care of it. Let's look at that again with the L. So with the L, you know, L is greater than E, F is greater than L. Sorry, L is greater than F, L is greater than H, L is not greater than L, but again, if you switch it to L is greater than or equal to L, then yes, that's still true, but here it's false, so then yes, doing that extra little equal sign basically takes care of that issue. And so now you achieve stability, okay? So yeah, that's all there's to it. Coding wise, like I said, if you really want to see an example of it, you can go on the page, so you can just see like a C++ example. It's basically going to be a loop that iterates through the entire thing, and then you keep a flag to know like which section is sorted, so you can search in that subsection. Okay, but you'll see that like for example, in the C++ implementation on the page, they have a for loop and a while loop. So it might be misleading and saying, oh, there's only one for loop, so it must be O of n. No, it's that inner while loop, right? You'll see it because you'll see two loops nested. That's how you know that the n squared is going to be there, even if you don't analyze the algorithm. That nested loop is like your sign. So yeah, and in fact, the outer loop is going from basically from 1 to n, which is just an n. The inner loop is going from 0 to j, and j is going to be kind of like the end of where you're at, of the sorted section per se, so the red stuff. So like I said, the first time around, you know, you're going to be doing n, and then you have a 1, a 2, a 3, a 4, all the way to the end. So if you actually compute this, you know, with this, then you will end up with essentially, I believe that what I wrote earlier, which I think is like n times, I can't remember if it's n plus 1. I think it's n minus 1 actually. I think this is what you end up with, which is going to definitely be n squared minus n, which doesn't matter. This is irrelevant. What really matters is this term. Okay? I think that's what you end up with if you do the math, like if you do the recurrence. Again, you only need to swap variable though. However, you know, this says sorting in place, and like if it's a linked list, then sure. But if it's an array, it can become kind of a bit of pain because like, you know, we're inserting things in the middle of the arrays, right? So like you have to shift things around for that, which you can do because like, you know, if you have something like here, like let's say you have, let's just imagine those are some letters that represent sorted letters and unsorted letters, right? So when you're grabbing this to insert it, regardless of wherever you insert it, like let's say you want to insert it here, because you took it from here, there's an empty spot technically here. You can shift things by 1 and then throw it in, right? And so now that's a sorted thing. And so you can do it in place. That's not a problem because you have the space every time. Like you take this one now, let's say that one's supposed to go right there. Well, you can just shift this by 1 because you have that empty space and you're good to go. So you never have a situation where you have to like make an entire new array. But it's not ideal because it's shifting, you know, imagine that this is supposed to go at the beginning. Yeah, well now you gotta shift everything by 1. And that of course that's time, right? So it can be done in place, but I think a new, like a linked list implementation would be good, because actually doing a new array doesn't even help you much either, because you still got to put it in the middle of things. So yeah, linked list would be the way. In fact, I would say either you do this in a linked list or you just don't do it, unless you're willing to do all that swapping, I suppose. Apparently, insertion sort is often is sort of sorted. No, I don't think so. Where did you see that? Because if the list is sorted, think about it. Think about how this will work if the list is sorted. Let's look at 1, 2, 3. If the list is sorted, insertion sort is going to look at this number and be like, okay, there's only one thing to move. So then you look at this one. So now it needs to find where this goes. So it needs to compare it with this first and then see that it goes there. And then for this, it needs to compare it with this, and then this. So it still has to do the n square comparisons. So, I mean, sure, you could write a code that says like, is the list sorted now? Like, you know, write a code that just checks the list once, but that's not pure insertion sort though, right? That's like your own version of insertion sort. And if even one single item is not sorted, then now you basically lost that capability. So I don't know. Geeks, I have a printed version of Geeks for Geeks, by the way. That's what I'm looking at here. But I'm trying to see if there's anywhere mentioning that. Boundary cases. Insertion sort takes maximum time to sort if elements are sorted. See? It even says it right there. This is from Geeks for Geeks. It says, boundary cases. Insertion sort takes maximum time to sort if elements are sorted. Oh, it says, I didn't finish reading. In reverse order. And takes minimum order of n when elements are already sorted. Oh, so I do see what you're saying. But why? No, I don't agree with that. I don't see how they're doing that. I don't know. I have to check on that. I don't know why they're claiming that. Like, let's look at their implementation in code. I want to see if they have that check that you're saying. They have insertion sort, I is equal to 1, I is less than n, key r, I is minus 1. You know, the way they have their code, they're not really checking whether something is sorted or not. They have a for loop that's going to go from I to n. And they have array I for that, which is going to start at 0, or 1 actually, and then go to 0. No, based on what I'm looking at, I disagree with them. See, I disagree with them. I say that it's still n squared. And like, if you go on Big O Cheat Sheet and all the other places, I'm pretty sure, like, actually, in fact, here, let's see what Wikipedia says on them. I wonder if they, because, you know, if Wikipedia also says it, then I'm going to start to question it. But let's see what Wikipedia will say. Wikipedia says, of and comparisons. Okay. I'll have to check on this. I'm not 100% sure now. I'll check on it and get back to you guys on it next time. It seems like they're doing an optimization. Here's what Wikipedia says. This kind of gives an insight. It says, the base case input is an array that is already sorted. In this case, insertion sort has a linear running time. During each iteration, the first remaining element of the input is only compared with the rightmost element of the sorted subsection of the array. But why would that get compared? I figured out what they did. Okay. this is interesting. Pretty ingenious, actually. Okay, I see what they're doing. Okay, so I'll show you an example of that with the with some numbers. Okay, so that's actually pretty cool. And no, they are absolutely correct now. I didn't know that. Somehow that had never come up. So let's actually do this with a random list that's unsorted. So let's do like a 3. Okay. So here's what they're doing. So the way I was telling you to do comparisons is like, okay, you have your sorted and unsorted section, like I said. So we have the red section. So let's just say we did that one already. And so we're looking at the 5, right? What I said to do is start from the left. And so check with the 1. It's bigger than the 1, so keep going, get to the 5. That one's good to go. And in fact, let's just, I'll just go because it's actually worthwhile explaining. So here, you got a 5 in there. That one is good to go. And then we go to the 4. And I said to start checking from the beginning. Look at the 1, look at the 5. It's less than the 5, so you go there. Okay. And then we keep going. So we look at the 8. We go 1, 1, 1, 8, right? So what I'm doing is I'm checking from left to right. Okay. What they do, the trick that they do to sort of fix that is they check from left to right. And if they do that, then they do achieve n, because here's what happens. So if I go and do this sorting, so 4, 1, 3, 2, and I do it that way. First I have a 1, so I just mark that as a sorted list. So now, instead of going from here to here, I'm just going to check here. So yes, it is greater than, so we're good to go on that one. So now, and I still keeping track of yeah, right. Sorry, I said it backwards. Yes, right to left instead of left to right. I'm left-handed, so that confuses me. Okay, so here, instead of going to check first with the 1 and then with the 8, they go from the 8 to the 1. So they say, okay, I guess they flip the sign, so they're probably going to say if 4 is less than 8, and in that case it's true. Then they look at the 1, and they say, is 1 less than 4? Is 4 less than 1? It's not, so therefore you put it in. Okay? Then you look at the 1 here, and again, instead of going like this, they're going to go like this. They're going to say, is 1 less than 8? Yep. Is 1 less than 4? Yes. Is 1 less than 1? No. But again, if you do the stable sorting, you do 1 is less than or equal to 1. So then you say yes, you keep going, you get to the beginning, and then you throw it in. Okay? So it's the same idea that I said. The only difference is, again, you're checking in the other direction. Now, this might seem like, why are you doing that? There's no reason to do that. But it's because of that optimization with the O of n that's going to do that. So again, with this, we check, is 3 less than 8? Yep. Is 3 less than 4? Yep. Is 3 less than 1? Nope. So then they must go in between them. So then again, you shift them up by 1. Like that. And then just throw it in there. Okay? Sorry, all the color things got messed up. And finally with the 2, you go blah, blah, blah. Nope, goes in there, and then you put it in. Okay? So it's the same thing. It's just you're checking in a different direction. You're checking downwards. And here's the catch. When you're doing this with a sorted list, you check this. It's like, nope. Okay, we're good to go then. What about 3? In the case before, I said, okay, you check the 1 and the 2, but here you're checking just against this. You see that it's greater than, so it must go there. You check this, you see that it's greater than, so it must go there. You check this, it's greater than, it must go there. And that is how they're achieving O of n. So I stand corrected. I'm very, very happy that you brought this up, because I actually, if I knew it, I had forgotten it completely. So, and in fact, I'm gonna, so I don't forget this in the future, I'm gonna write that down. And then the sheet that I have at the front. Okay. Yep, it does take advantage of that. So pretty interesting and pretty cool. Still, it's a slow algorithm, but at least you know, it has that. It's pretty interesting idea to do. So I respect that. You'll see a mention about whether something is online or not. I guess I should mention what that means. When they talk about online algorithms, the first time I actually came into that term was back when I was learning machine learning, online learning versus offline learning and whatnot. But really, when you hear whether a sorting algorithm is online or not, is that you don't, like, when you have a massive list, like I'm talking about really big list, it's not cool to load that into main memory because it's like, it doesn't fit. So you only want to load a chunk of it at a time and then another chunk. So you do like a batch sort of processing. With an online learning algorithm, it's written in a way that it allows you to do that. Some algorithms require you to have access to the entire data set at once to be able to work with it. An online one allows you to just have a piece of it, work with that piece, and then throw that away and load another piece. With bubble sort, you can do that because, like, if you're sorting this huge, massive bubble sort list, like with 1 million numbers, say there's like 1 million numbers here, but you can only load like 10,000 at a time. You can load the first 10,000, do your bubbling up for 1 digit, and then unload that, and then load in the next 10,000 in. Continue your bubbling up there, unload that, load the next one in, right? So that allows sort of bubble sort to kind of be like an online sort of algorithm. And the same thing here, you know, you only load the region you're working with. So like maybe part of the sorted list and part of the, I guess if you're doing this in new backwards way of doing that, then maybe you load like a piece of this list and then you load the next number you're gonna work with. And so now, you know, you start checking it against all of this, and if you need to go further, then you can load that in, right? But you don't need to have the entire thing at once. Useful for, again, when you're dealing with lots of data, to not have to load everything at once. So that's where online comes from, the term online. But I don't really see used often with this sorting stuff. With machine learning, it's useful. Don't worry about what binary insertion sort is and whatnot. Yeah, BOGO sort would actually require you to load the entire data. So that would definitely not be like an online thing. We just have to load everything at once to check it. I mean, yeah, because how do you randomly generate the same numbers to mix them up? You need to load them all at once. Well, I guess you could do a piece. You could randomize the first 3 numbers and see if they're sorted, and then randomize the next 3 numbers and see if they're sorted. But to do true BOGO sort, you can't re-randomize them until you check the other ones, I guess. Yeah, like BOGO each batch, essentially. Batch per BOGO batch. Yeah. Okay, we got one more to go today, and then we will be good to go. Because we got the last of the easy ones, which is selection sort. And then from there, next class we'll do merge and quick, which are those are actually the good ones. So that way, at least at home, when over the weekend, you can start out, you can do the first 3 and then leave merge and quick for Tuesday. And when is this assignment 5 due? Let me make sure, because I do want to give you a weekend after that. Oh yeah, it's due October 13th, so we're fine. Yeah, so that gives you, so you can start this weekend with that, and then next weekend you can finish the quick and merge. Okay, so selection sort. Very interesting. I actually really appreciate the whole O of n thing for that. Okay, so moving on to the next one here, selection sort. Let me look at my complexities for that one. So that one I have n squared for everything as well. Let's see what Geeks for Geeks says on that. They don't even have a best case option for that one. But here, let me link you to the Geeks for Geeks for them. Okay, so selection sorts. Yeah, okay, sorry, I had to like refresh my mind. Okay, now I remember. Okay, so selection sort and insertion sort are kind of similar. in the way that they work, but different at the same time. So the basic idea with selection sort is you're going to have a list of letters. So this time let's do, here, let's do your name now. That's what we're sorting. Okay, so in this case, what I want to do is I want to sort this, right? With selection sort, what I'm going to do is I'm going to look at the entire list once, and I'm going to keep track of the smallest letter if I'm sorting in descending order, okay? So in this case, I'm like looking at C, and I'm like, C is the smallest letter I've seen so far. I look at O, and I'm like, C is still the smallest letter I've seen so far. So here I'll point to the top arrow, meaning where I'm looking at. So right now that's the smallest. C is still smallest, C is still smallest, C is still smallest, A is smallest than C. So now I found a new smallest. So I mark that there. And then I go to the rest. And once I get to the end, I'm like, okay, I found the minimum. Okay, and you can all code how to find a minimum. You just put a loop and keep track of the index of the minimum. If you find a new minimum, you put it in. If you want to duplicate, if you want to keep things stable, then you keep the first instance that you found, right? So we'll see that with the O later on. So when you do that, if you want to make the algorithm stable, you're going to have to make a brand new list beneath it or somewhere, and then store the sorted array there. If you don't care about stability, all you got to do is swap the first element with that one. So if I do this, then I am good to go. However, if you do it that way, you will lose stability. So if you make a new array, then you can just go ahead and throw in your A here, and then keep going. That will be stable. If you do it in what's called in place, then you will lose stability. Okay. So, but let's do the in place one because that's the traditional one. So in that case, we do that, and also just kind of similar to the insertion sort, you keep track of what is considered your sorted list versus your unsorted list, right? So we kind of marked it as a red. That way, when you're looking for your next minimum, you don't go looking there because otherwise you'll keep finding the A and then never finish. So in that case, we're going to start from here, okay? So we always just set the first thing we find as minimum because that's the first thing we've seen. And then we keep going. We have another O, but again, because, well, at this point we've lost stability, so it doesn't matter much. But if we were doing the other method, we want to make sure that this stays pointed to the first instance, which typically when you're finding minimums, that's what you do, right? You only update if you find a new minimum. You don't update if you find a duplicate. Like you just say, if this is less than this, then update it. Otherwise, you don't put that less than or equal. There's no reason to do that. It's more work. So you keep going. You see the C, you're like, oh, the C is actually smaller than the O, so you mark it as a new minimum, and you keep going, and then you finish. So now you're going to swap this with the next available slot, which is where the O is. So you take this, you put it there, and you put the O there. Okay? So now you mark this as part of your sorted array. All right, so the next spot you're going to be working with is going to be this one. So again, this is the first O you see. So you're going to look at that. No, smaller. Okay, perfect. So we found a smaller one. And then, of course, you finish and you see that that's the smallest. So you're going to swap that with the O. So erase the O, put that there. Of course, you got to put a temporary here, just like any of the other sort functions. You need that temp auxiliary space. And then you're good to go with that. And I hope you get the idea here about this, but if not, let's just kind of finish this. So P small, but then O is smaller than P. And then you finish. So then you erase that. Like that. And then you mark that as good to go. And of course, how am I marking this in code? I'm just keeping another index called like either at the last digit or the first non-sorted, and just call it like end of sorted or something. Just an integer that you keep track of that. Okay, that's just what you do. And that's the one that you're going to probably set +1 to be the next available spot to sort. So you just take this value +1 it, and that's where you got to start at the next iteration. So you go there, gets updated to that, and then you go in and you swap them. Then you increase this one, the end of sort, you increase it by 1. And then you set these two +1 of end of sort, and then here it gets updated to that. Oop, I moved the R. So you swap that, and then you increase this by 1, and then of course you just have one thing left. So you go there, swaps with itself if needed be, and then you are finished. That's selection sort. It's not a hard one either. This one's actually, I would say, easiest to code when you're coding this. Like, even I would say even easier than bubble sort to code. Like, bubble sort requires a little bit of thinking with the bubbling to make sure you don't screw up the indices and whatnot. But with this one, it's just a loop that you're going to run, find the minimum, and then actually insert that in the next available index. Of course, it might be, you might think, oh, that's fast, but no, because you're doing a bunch of checks. You're like check, 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 check. Every time one less than the other one. So this is going to be another one of those scenarios where it's going to be something like n times n minus 1, and it's ultimately going to be n squared times complexity. And I believe everywhere I've seen this one does do n squared for everything. But, yeah, because I mean, like, if you give it a sorted list, like this is saying, and then this basically is going to be the smallest number, but you still got to check all of these to see that it's the smallest. And then you're like, okay, that's good. And then you check this, and you got to compare them with all of them to find out that it's the smallest. So even if you do have the smallest number, that's actually, there's not much you can do other than just keep going. So we are out of time now, but the one good thing about selection sort that I have here is that it never makes more than O(n) swaps. So if like, let's say you have a really old computer that for some reason, like the hard drive is busted, and like it takes a long time to do a swap. If you really want an algorithm that looks at it, compares the most amount of times you want, because it's n squared, but it does the least amount of swaps possible. So like, if you're playing a game with someone and they ask you like, okay, I would like you to sort this list with the least amount of swaps possible. That's a really hard problem, by the way. But if you want a sort of a quick shortcut to an ideal that might not be the perfect one, but more than likely will be the quickest one you can come up with on the spot, is going to be the selection sort. Okay, so just move the minimum to the beginning, and then move the next minimum, and you'll finish it in n time. There might be a faster way of doing it, by the way. I've seen some code somewhere on the internet that's fast, that like requires a lot of recursion and things to basically to kind of find the shortest sort of tree for that. But it is possible to potentially do in less moves than n moves. You just leave some things in the right spots, and you don't need to move them, I guess. But yeah. That will only make n swaps, and you'll be good to go. So I guess if swaps is all you care about, then selection sort is your way to go. But again, swaps are cheap to do. It's about the overarching time to not just do the swaps, but also do the comparisons, which takes the longest time in a sorting algorithm. Okay? So again, you might be like, wow, all these algorithms suck. I'm not saying they don't, but I'm saying that they're good to know because they do have sometimes some cases of them that are useful, but more than likely the reason to understand them is because it makes you better at understanding code and analyzing code, and taking ideas that are simple and implementing them. You going home and coding these things is a good practice for you, so that when you have to code more complicated stuff like quicksort, you got more practice of taking an idea from happy pictures to actual code. Because even the simplest of things can be hard to actually translate to code if you don't have practice with it. Okay? So that's it. Next time we will continue with video 9. All right. So thanks for watching, everybody, and hope you all have a good weekend. And I'll see you on Monday. Almost done with September, actually. We're also getting slightly close to the first exam, so we'll talk about that at some point. Don't worry about it for now. Worry about your assignments. So see y'all. Have a good weekend. Bye. Thank you.